In this video, we are going to look at how explicit solutions of linear constant coefficient ODEs help us understand stability. Let's start with one of the simplest linear differential equations, x dot equals ax. To solve this, we need a function x of t, where differentiating it gives us a times the same function again. Exponential functions have exactly this property. The derivative of e to the at with respect to t is a e to the at. So, if we try x equal c times e to the at, then we get x dot equals a c e to the at, where c is a constant. But c e to the at is just x of t, so this gives us x dot equals ax. This is why exponential terms appear naturally in solutions of linear differential equations. Now, let's use the exponential form in a homogeneous second-order linear ODE with constant coefficients. Here, we have x double dot plus 3x dot plus 2x equals 0. Because exponential terms appear naturally in linear constant coefficient ODEs, we try a solution of the form x of t equals e to the at. When we differentiate e to the at, the exponential term stays the same, and the result is multiplied by a factor of a each time. So, after substituting into the differential equation, every term contains e to the at. We can factor that exponential term out. Since e to the at is never exactly 0 for any finite t, the remaining factor must be 0. That gives a squared plus 3a plus 2 equals 0, which is called the characteristic equation. Its roots give the values of a that appear in the exponential solution terms. A root is a value that makes an equation equal to 0. For the characteristic equation a squared plus 3a plus 2 equals 0, we factor the left-hand side into a plus 1 and a plus 2. So the roots are a equals minus 1 and a equals minus 2. In this context, the roots have a specific meaning. They tell us the values of a in the exponential terms of the solution. So, a equals minus 1 gives a term involving e to the minus t, and a equals minus 2 gives a term involving e to the minus 2t. In other words, the roots tell us the values of a that appear in the exponent. Now that we know roots give the values of a in the exponential solution terms, we can ask what different real values of a mean. If a is less than 0, then e to the at decays over time. If a is bigger than 0, then e to the at grows over time. And if a equals 0, then e to the at equals 1. So the term stays constant. Therefore, real roots tell us whether exponential solution terms decay, grow, or stay constant. What happens if the characteristic equation has a repeated root? In this example, the characteristic equation is a squared plus 2a plus 1, which factors to a plus 1 squared equals 0. So, a minus 1 is a repeated root. A single root at a equals minus 1 gives the exponential term e to the minus t. But because the root is repeated, we also get a second solution term, t times e to the minus t. More generally, repeated roots introduce powers of time. A double root gives an extra factor of t. A triple root also gives a term involving t squared, and so on. Let us quickly check that t times e to the minus t really is a solution of the ODE. The ODE we are checking is x double dot plus 2x dot plus x equals 0. If x equals t times e to the minus t, then x dot equals 1 minus t e to the minus t, and x double dot equals t minus 2 e to the minus t. You may want to pause the video here and substitute x, x dot, and x double dot into the ODE. If you do that, the terms cancel and the expression becomes 0. So, t times e to the minus t satisfies the ODE. For this ODE, the characteristic equation is a squared equals 0. So a equals 0 is a repeated root. From the repeated root idea, a double root gives the term e to the at and t times e to the at. Here, the repeated root is 0. So e to the 0 times t equals 1, and t times e to the 0 times t equals t. That means the general solution term has the form x equals c1 plus c2 times t. If c2 is not 0, then the c2 times t term grows linearly with time. This is a simple example of algebraic growth. So, repeated 0 roots can lead to algebraically unstable behavior. The response can drift away over time through algebraic growth. To recap, the key idea is that characteristic roots tell us how the solution terms for the linear ODEs we are considering behave. In this video, we focused on real roots. A negative real root gives decay, a positive real root gives growth, and a 0 root gives a constant term. We also saw that repeated roots can introduce algebraic growth. For complex roots, the same growth and decay principles apply to the real part of the root. To connect characteristic roots back to stability, we think about deviations from equilibrium. We can write x of t equals xe plus delta x of t. This means the response is the equilibrium value plus the deviation from that equilibrium. If the deviation delta x of t goes to 0, then x of t returns to xe. This corresponds to asymptotic stability. If delta x of t remains bounded and does not go to 0, then the response stays near the equilibrium but does not settle. This corresponds to marginal stability. If the deviation grows in magnitude, then x of t moves away from the equilibrium. This corresponds to instability. So, when we use roots to discuss stability, we are asking how deviations from the equilibrium point behave over time.